So good morning, good afternoon, good evening, everyone. I'm James Trussler from the University of Cambridge, and today I'd like to talk about how we can use the stellar metallicities and stellar ages of galaxies to infer the role of environment in galaxy evolution and galaxy quenching as I discuss the weak imprint of environment on the stellar populations of galaxies. So as excellently put forth by the previous speakers today, the environment within which galaxies reside has long been thought to play a role in shaping their evolution. And indeed, with the advent of large spectroscopic galaxy surveys, by tapping into their statistical power, we've been able to start to disentangle the separate roles of mass and environment in driving galaxy evolution. And here I show you a notable example. It's this iconic plot from Peng et al. 2010. On the horizontal axis, I show stellar mass, and on the vertical axis is the local overdensity, really characterizing the environment within which galaxies reside, and it's color-coded by the quench fraction. So what's clear from this plot is that you go from left to right. If you increase stellar mass at fixed environment, the quench fraction of galaxies increases. And all the same, if you stay at a fixed mass and go vertically upwards, if you increase the overdensity, the quench fraction of galaxies increases as well. So it's quite clear from this result that both mass and environment are key drivers of galaxy quenching. But actually, if you just focus on the star-forming population, actually, a different picture emerges. Here we have the color coding by star formation rate for the star-forming population. And although there's an increase in star formation rate with stellar mass as you go from left to right, there's no clear environmental dependence of the star formation rate. So for galaxies in Sloan, when we're characterizing the overdensity, then we find that the star formation rate is roughly independent of environment, although, as Bianca put forth earlier today, is that if you really focus on the densest regions, the clusters, there are indications of environmental suppression of star formation there. And so that's a key point of my talk today, is that while the environment in which you reside really matters depending on whether you're star forming and passive in terms of quench fraction, provided that you're just looking at the star forming population, for instance, their properties are roughly independent of environment. And so for this talk, I'd like to focus further on the environmental dependence of the stellar populations of galaxies. And over 10 years ago, Pasquale et al. Investigated the scaling relations of stellar mass, stellar metallicity on the left panel, and stellar mass, stellar age on the right panel. And shown in solid curve is a median trend in black for satellites and in gray for centrals. And the key point is that you find that the satellite population is both slightly more metal rich on the left panel and slightly older on the right panel than centrals. So evidently, the environment within which galaxies reside is playing a role in driving their star formation and chemical enrichment histories, and that this effect is strongest at the low mass end and decreases with increasing stellar mass. So today I'd like to revisit this result now using the power of Sloan Digital Sky Survey Data Release 7, which has obtained optical spectra for 1 million galaxies in the local universe. After applying cuts in redshift and signal to noise to ensure that the stellar population parameters we derive are reliable, we're left with 80,000 galaxies after these cuts. We use the mass-weighted stellar metallicities and stellar ages from the Firefly spectral fitting code, which uses a linear combination of simple stellar populations to derive these parameters. It aims to fit both the shape and the absorption features of the optical spectra. And for our analysis for the environment, we're using the group catalogs from Yang et al. 2007. We define centrals to be the most massive galaxies in their groups, satellites are all the remaining galaxies. And so furthermore, we classify galaxies using the bimodality in the star formation rate stellar mass plane. So star forming galaxies at relatively high star formation rates, passive galaxies at relatively low star formation rates, and green valley galaxies are in between the peaks in this distribution in this plane. They're currently in the process of quenching. And so if we undergo the same analysis as Pasquale et al. 2010, we actually obtain a similar result, namely that satellite galaxies shown in solid are slightly more metal rich than centrals shown in dashed with this same mass-dependent trend. But over the intervening years, we've come to learn a lot about the distinct properties of star-forming and passive galaxies. Not only are they distinct in terms of their star formation activity, in terms of their morphology, in terms of their colors, and indeed their ages, so too are these galaxies distinct in terms of their chemistry. Green Valley galaxies shown in green and passive galaxies shown in red are considerably more metal-rich than star-forming galaxies shown in blue of the same stellar mass, as shown by the stellar mass-stellar metallicity relation here. And so this indicates that galaxies actually typically undergo a considerable amount of chemical enrichment during the transition from star-forming to passive, which I'll return to later in this talk. So if we take into account the distinct chemistry of star-forming passive galaxies, and also recognize that the satellite population shown in red here is actually relatively more quenched than the central population shown in blue, then it could very well be that this offset that we're seeing between the overall populations of centrals and satellites in the left panel is really just driven by the fact that the satellite population consists of more of these metal-rich passive galaxies, while the satellite population is relatively more quenched, while the central population consists of relatively more of these metal-poor star-forming galaxies. So if we want to disentangle the effects of the environmental dependence of quench fraction from the inherent dependence of stellar metallicity and environment, it's important to separate the star-forming Green Valley and passive populations. And that's what we've done here in the right panel. And I hope that you'd all agree with me upon comparing the left to the right panels, is that after making the separation, the difference between centrals and satellites shown in dashed and solid respectively becomes considerably smaller, less than 0.03 dex. So the satellite population is in fact only marginally more metal-rich than centrals of the same stellar mass. And so then that leads me to a key point that I like to make, is that while the environment is clearly playing an important role in the quenching of star formation in galaxies, it appears to only play a relatively more minor role in shaping the actual stellar population parameters of star forming and passive galaxies. And we can look at this environmental effect in a bit more detail here. On the vertical axis now, I'm showing the difference in metallicity between the central and satellite populations. And so while the overall population clearly had this mass-dependent trend, after you make this separation, you find that there's no actual clear trend of stellar mass at all, and the effect is weak. It's less than 0.03 dex. And so that's why I would strongly advocate for the separation of star-forming Green Valley and passive galaxies when environmental dependencies of galaxy properties are investigated, as otherwise both the environmental effect could be exaggerated, and indeed the mass dependence of these environmental effects may be misrepresented. And this is especially the case when these physical properties are starkly different for star-forming and passive galaxies, like the stellar metallicities I mentioned earlier, but also the galaxy sizes we've been discussing earlier on Monday, and indeed the stellar ages. And so when it comes to the stellar ages, I just like to raise the following point, is that again, if you're comparing the overall populations of centrals and satellites, you find an indication for a strong environmental effect, suggesting that the environment is playing a significant role in shaping the star formation and formation histories of galaxies. But after making that separation again, the star forming Green Valley and passive, you find that the actual environmental dependence is a lot smaller, with the satellite population being only marginally older, less than 0.5 gigayears, than that of the centrals of the same stellar mass. But with the statistical power of Sloan, we can go beyond just the central satellite comparison. We can go to further environmental measures. So here I'm showing the overdensity. And so it's the stellar mass, stellar metallicity relation for the overall satellite population, now further divided into quartiles of the local overdensity. So going from low density regions in blue all the way out to high density regions in red. And what you'll see is that there's a steady increase of stellar metallicity with increasing overdensity of about 0.1 dex. But we should, of course, bear in mind that the quench fraction of the satellite population also increases as you go to higher overdensity. So again, it becomes important to separate the star-forming Green Valley and passive populations if we really want to see the inherent dependence of metallicity on environment. So that's what I show here. I showed the overall trend for satellites in the top left. In the right panel is the trend for star-forming and passive satellites, in the bottom left panel for Green Valley. And so just to make it clear, after making the separation, we only find a small but steady increase of stellar metallicity with increasing overdensity for the passive population, so less than 0.05 dex. We find a similar weak trend for the Green Valley satellite population as you go from the low density regions in blue to the high density regions in red. There's at most a 0.08 dex increase in metallicity. But interestingly, we find actually no indication of an environmental dependence for the star-forming satellite population. So to summarize, although you find strong trends when looking at the overall population of satellites, after you make this separation, really disentangling the environmental dependence of quench fraction, you actually find that the stellar metallicity of galaxies only depends rather weakly on overdensity for the passive and Green Valley populations, and indeed no environmental trend for the star-forming satellite population. Now, in contrast to this, actually, if you just focus on the central population instead of the satellite population, in that case, you find no indication of environmental trends at all, neither for the overall population nor for the star-forming Green Valley and passive. And we've also investigated other environmental parameters in our analysis, so projected distance and halo mass, and we find qualitatively similar but weak trends throughout. So to put these environmental trends that we found into the context of environmental quenching, I'd just like to go back to the chemical transformation that takes place during the transition from star forming to passive again. By comparing the levels of chemical enrichment in star forming and passive galaxies, we can actually infer things about the typical quenching process in galaxies, as the amount of chemical enrichment that takes place during quenching depends on the quenching mechanism. And the main idea behind this approach is that if you have your star-forming galaxy, it's growing, it's increasing in stellar mass, and indeed growing in stellar metallicity as it forms new stars. But this increase of stellar metallicity with respect to stellar mass during the main sequence evolution is not very steep.
4.5 minutes left.
Okay, that's great. So it's not very steep because while these galaxies are synthesizing new metals, they're also accreting pristine metal poor gas from the intergalactic medium. So the slope here during main sequence is not very steep. However, if we consider galaxies that undergo quenching, and firstly we'll consider quenching by sudden gas removal, forming a passive population in that way, and this may be triggered by ram pressure stripping, for instance. Well, in this quenching scenario, very little additional stars are formed during the quenching phase, and so you only expect there to be a relatively small increase in stellar metallicity during quenching. On the other hand, if you have quenching by starvation, this is where the accretion of fresh gas from the cosmic web, from the circumgalactic medium, is halted. Well, in this scenario, the galaxy continues to form additional stars during the quenching phase. And additionally, because we no longer have this accretion of pristine gas, the increase of stellar metallicity with respect to stellar mass is a lot steeper than it was during the main sequence phase because there's no longer this dilution effect. So you expect there to be a relatively large stellar metallicity increase during quenching by starvation. And so the key principle here is that the stellar metallicity increase during quenching depends on the mechanism. It's small for quenching by sudden gas removal. It's large for quenching by starvation. Now, observationally, we can't actually measure the stellar metallicity increase during quenching directly because we can't track the evolution of galaxies across cosmic time, but we can infer this increase indirectly by comparing the stellar metallicities of star-forming and passive galaxies. Small stellar metallicity differences are indicative of quenching by sudden gas removal. Large stellar metallicity differences are indicative of quenching by starvation. And so really by using the stellar metallicity difference that we can observe as a proxy for the prevalence of starvation as a quenching mechanism in galaxies, we can really determine whether it's starvation or gas removal that's driving galaxy quenching. And so to do this, I've developed a novel chemical evolution model that aims to simultaneously reproduce both the high stellar metallicities of local passive galaxies shown on the left and their low star formation rates shown on the right. And to do that, we assume that galaxies quench through a combination of starvation, so no gas accretion, and gas removal, where the outflow rate of the gas being expelled is proportional to the star formation rate, and the strength of that expulsion is given by this effective mass loading factor. So I show our final results here. It's the mass loading factor on the vertical axis against stellar mass on the horizontal. Excuse me?
2 minutes left.
Okay, 2 minutes on the horizontal axis. And this is for centrals on the left and for satellites on the right. And again, they've been further separated into quartiles of the local overdensity. So low density regions in blue, all the way out to high density regions in red. And so the key point on the left panel for the centrals is that we find that this mass loading factor is actually independent of the local overdensity for centrals. And so what that implies within our framework is that the starvation that's responsible for quenching centrals is predominantly driven by mass-related phenomena, and it's not driven by environmental processes. In great contrast to this, as we focus on the right panel for satellites, we do find an environmental dependence of the mass loading factor decreasing with increasing overdensity for satellites. So while the quenching of satellite galaxies in dense environments shown in red is relatively more starvation dominated than for satellite galaxies in low density environments shown in blue. And so what this indicates from our results is that starvation, rather than gas stripping, actually becomes progressively more important in quenching satellites in progressively denser environments. So I'd like to leave you with my summary slide. We've been able to use the statistical power of Sloan to investigate the environmental dependence of the stellar population in galaxies. And really, after making these separations into star-forming green valley and passive, we find that these environmental trends, just like Anna Galazzi had said earlier on Monday, are actually rather weak after making the separations between centrals and satellites and looking at further trends with the overdensity. So thank you for your time, and I'm happy to receive any questions.